So I try and clench and release one hand as fast as possible, and that sounds strange because I can't actually move the hand, but I can still visualise doing it.
Paralysis is often a result of spinal cord injuries, which prevents messages from the brain being sent to the rest of the body. And in some severe cases, that can be non-physical movement from the neck downwards. So I've come to Imperial College London to see how scientists are decoding brain signals, effectively allowing people to control devices with their minds. At the Brain and Behaviour Lab, Dr. Aldo Faisal and his team study machine learning systems and biological brains and how they can both learn from one another.
It all began with the question that how can we use the power of artificial intelligence to help our biological intelligence if it's affected by disease or injury. And so this brought about the development of brain-computer interfaces that are going beyond what is currently capable by exploiting the power of AI to better understand and automatically understand what the brain is thinking, to translate that into actions for the brain.
The human brain is made up of about 86 billion neurons or nerve cells, which are largely responsible for the way we think, feel and act. Each connection sends signals or fires at an average frequency of 4 to 10 Hertz, or 4 to 10 times a second. Some even fire at a rate of 3 to 400 Hertz. This is a huge amount of output, so to pick out certain information within a mass of noisy signals is a difficult task.
It's incredibly noisy. To give you a sense, it would be probably like whispering in a typhoon or something like that. It's barely audible, and you're really trying to pick out of these very fast, very noisy signals something.
Artificial intelligence has the ability to sift through all of the data and spot patterns and trends and filter out the noise. But before AI begins spotting patterns and trends, electrical brain signals must be tracked and recorded. That's done using an electroencephalograph, a technique that requires electrodes to be placed all over the scalp. The team working on developing the brain-computer interface technology will be competing at the World Championship of Robotic Systems for People with Disabilities, or Cybathlon. Scientists team up with pilots, people with real disabilities who test and advance their new technology. Pablo Ortega San Miguel is completing his PhD whilst leading the BCI discipline at Imperial College. Brain-computer interfacing, what exactly is that?
So a brain-computer interface is a device that translates your thoughts, if you want to say, or your brain signals into commands that a computer can use to do something, basically. So for us, you can think of the technology as a complement to our daily life, like you could maybe set your alarm using your brain. But I find more meaning for it for people that actually cannot interact with their surroundings.
One of those people is Tom Nabarro. He's been unable to move all 4 limbs since a snowboarding accident in 2007.
Here we have Tom, our pilot, and our team for the Cybathlon 2020.
How do you feel about being part of something so cutting edge and pioneering?
For me, it's been an amazing experience. The event itself is just, it's only just started. There's never been anything really like the Cybathlon. People call it the Cyber Olympics, and it is cutting edge, and it's something that has only just happened because now we're at a stage where there's so much assistive technology. It's becoming such an important part of so many people's lives, and that they're making an event about it.
64 electrodes are being attached to their assigned positions, and it's really important that this is done meticulously and carefully because this is where all the data is collected. Data about brain signals corresponding to movements. Each electrode detects the electrical activity of thousands of neurons that are active or firing in the brain. In between the signals and the electrodes is about 1 centimetre of bone, skin and hair, which makes the signals harder to detect. The water-based gel is syringed at the electrode tip to improve electrical conductivity and their detection of these signals, which are represented as waves on the screen. All this data is stored for the AI to analyse.
As you syringe this very conductive gel into the connections between the electrodes and your scalp, you're seeing the lights turn green.
The next stage of the process is the calibration of the game being tested today.
So what exactly are you setting up?
It's the example game, and the idea is that if I'm watching the video of game, I can practice making the signals that I would if I was playing a real game.
What Tom needs to do is repeatedly imagine certain actions so the computer can identify and learn them as being specific instructions for controlling the virtual wheelchair. These imagined actions are known as motor imageries, and the difficulty is in keeping them clear and then repeating them in exactly the same way.
It's quite strenuous. I mean, you just have to repeat an imagery, so you're just trying to think and concentrate. So I try and clinch and release one hand as fast as possible, and that sounds strange because I can't actually move the hand, but I can still visualise doing it.
Once this process is complete, the computer is able to create representations of what these imagined actions look like, or which areas of the brain have been active.
So what are these pictures showing us?
So these pictures are showing us Tom attempting to move his left hand and his right hand. And we can see clearly that the power of the brain activity decreases when he's trying to move his left hand on the right hemisphere and the other way around.
The right side of the brain controls movement on the left side of the body, and the left side controls the right side, shown here in red as increased and decreased brain activity.
Okay, so these patterns are then fed into an algorithm that will look at those trends.
Yeah, and learn these differences basically.
Tom is now ready to practice playing the game in a dry run. Staying focused on specific thoughts is exhausting, but necessary for providing the AI algorithm with consistently clear signals.
We did not use data effect before, so the model could be unstable. It's fine.
It still needs some fine-tuning, but it's amazing to see him starting to control the virtual wheelchair by thought alone.
And it really is an emphasis on thinking, because with someone like Tom, he can't carry out actions. So it's really about how he thinks that counts.
Correct. We're trying to capture his intentions, and we can capture that through methods called motor imagery, where he imagines that he makes a movement, and say with his toe, and we capture that brain activity. But sometimes it turns out that it's easier to make him imagine other things. For example, thinking about a sound, and that gives you a stronger command.
How soon can we see this technology being used?
Well, the question is ultimately how poor of an interface are you happy with? To give you a sense, so Tom is fully paralyzed, so he has no other way of moving. So accepting that a system such as a state-of-the-art system maybe get 1 in 3 or 1 in 2 decisions right is acceptable. But imagine you were to type on a keyboard that gets every second letter wrong. It would not be acceptable. So here it's really where we believe AI can really push it to the next level.
So far, Tom has been using the headset at Imperial once a month. The next step is to use a wireless headset, which can be fitted quickly without much prep work. This would allow people like Tom to provide a lot more data from the comfort of his own home.
So it's tight. Just let me know when there's enough pressure. I'm just gonna do this in some of the electrodes, okay?
It's almost like getting a head massage.
And relax as much as you can. Yeah, so basically these are your alpha waves here.
Wow.
So now you just move your right hand. Yeah, cool. So this is basically what you can see, right? So basically when you're moving your right hand, you have very low power on your left hemisphere, high power in your right hemisphere around these areas. So now if you want, you can try the same but thinking about doing it. So these are very weird and alien sensation actually, because not many people actually try to do this in their everyday life. But what you can try and do is kind of try to feel how it feels when you move your hand but without moving it.
Trying to do what Tom did is really difficult, and as you can see, my signals are unclear. To achieve clear signals will take a lot of practice. Feeding the AI with more data to sift through, allowing it to filter the noise and identify the pattern of signals in my thoughts. I must say, continuously imagining an action requires a lot of concentration.
There seems to be so much data here. I mean, how long would I have to be hooked up to this before the machine learns?
So there are two aspects of it, because like one thing is how well the artificial intelligence is able to recognize the patterns, and the other one is how well you can generate those patterns.
Hi, how's it going?
Good, I think.
We really believe that the way forward is to let algorithms learn from the data how to best understand the data. That's how we do it ourselves. We learn from experience how to do things better. And that allows us to push the boundaries of what's possible further ahead. The brain is very complex, and we're just really starting to scrape at the edges of what we can start decoding. But already we have made a huge leap forward. You know, you've just put this headset more or less on in just a minute. So we think this will not only make it easier for patients to use it on a daily basis, just pop it on their head, but also it means that we as consumers can benefit on a more sympathetic and in a standard way.
Machines are learning quickly from the way we think, and the technology is advancing rapidly. The challenge is to transfer its use to real-world assisted devices that will improve the lives of people like Tom. Overloaded with science yet? If you like what you saw, then like, comment and subscribe by hitting the bell button below. Thanks for watching.